What is the shear code in quantum error correction? Imagine trying to keep a delicate message safe from noise and errors in a noisy environment. That's similar to what quantum computers face with their fragile quantum information. Today, we're going to uncover how the shear code helps protect quantum data from errors that can happen during calculations. The shear code is a method that encodes one logical quantum bit, or qubit, into 9 physical qubits. It was the first quantum error correction code ever created. Its main goal is to protect quantum information from 2 types of errors: bit flip errors and phase flip errors. A bit flip error happens when a qubit state flips from 0 to 1 or vice versa. A phase flip error changes the phase of the qubit, flipping the sign of its quantum amplitude. Both errors can mess up calculations if not corrected. Quantum information is very sensitive. Small disturbances like noise or decoherence can cause errors that ruin the results. The shear code tackles this by spreading the information across 9 qubits in a special pattern. It combines 2 simpler codes, a 3-qubit bit flip code and a 3-qubit phase flip code. The code applies the 3-qubit bit flip code to each of the 3 qubits in the phase flip code. This way, it can detect and correct both error types at the same time. Error detection works by measuring something called error syndromes. These measurements use extra qubits called ancillas. Importantly, they do not directly measure the logical qubit itself. Instead, they identify if an error has occurred, what kind it is, and where it is. Once detected, specific corrective operations are applied to fix the errors and restore the original state. This process keeps the quantum information intact and ready for further calculations. Mathematically, the logical qubit states in the shear code are written as superpositions involving triplets of qubits. These triplets are arranged in states like 000 and 111. The code uses stabilizer measurements to check for errors without disturbing the quantum information. Because of this structure, the shear code can correct any single qubit error, which is essential for reliable quantum computing over time. In the bigger picture of fault-tolerant quantum computing, the shear code was a major step forward. It showed how redundancy and clever encoding could protect quantum data. While newer codes like surface codes are more efficient, the shear code remains a key example of how quantum error correction works. Its principles continue to influence how hardware and software are built to run long, complex quantum algorithms reliably.